So, three forces trying to spin this wrench. Which one causes the biggest torque? F of B, if we assume that A and B are the same force, which arrows look pretty similar, so we can assume that, right? What about C? No torque at all, okay? Here's three forces acting on a rotating rod or cylinder, whatever it is, I don't know. This point labeled O is the rotation point, okay? So in this case, first, what can we say about this 30 Newton force? Does it cause any torque?
No.
Why not?
It's through the center.
Passes through the center, right? Regardless of how big of a force it is or what the angle is, this force is going to cause no torque because it passes through the center of rotation.
Even though it's not parallel?
Even though, well, yeah, it's parallel to the lever arm, like, because the lever arm here, well, even if you think about it too, if you think about the formula, right, the formula being T is equal to F times D times sine of theta, right? D is the distance from the center of rotation, right? Here, where's the force being applied? At the center of rotation, so that D value goes to 0. Does that make sense?
What exactly is rotating? Like, I can't
Well, oh, it's, yeah, no, it's kind of like it's kind of so it's kind of like this.
Like, would you consider the center of
We're
rotation?
clamping it on this end right here, and we're doing this. Does that make more sense? Okay. So yeah, clamping it over here on this end, and then so that force is basically like this, which won't cause any rotation. But now there's two other forces that aren't being applied at the center of rotation. So in order to answer this question, what would we have to do? Okay, some calculation involved, right? Here, if we look at the 25 Newton force, right, is that whole 25 Newton force going to causing torque? No, right? You got this here, right? You got this here, okay? Which of these components is causing the torque in this case? The vertical one, this one right here, right? This one, through the center of rotation, this one won't cause any torque, okay? Does that make sense?
Which part? I'm still confused why that one doesn't apply anything. It has some vertical.
Except yes, I mean, here, both of these forces though, right? This one goes through the center of rotation this way. This one goes through the center of rotation this way. Does that make sense?
So wait, that side's not so?
Nope, over here.
Are you supposed to?
Because it's labeled O, and I just.
Whoops, sorry.
But did you calculate this out or no?
Yeah, that's 257.5 and 15.6.
Okay, so 257.5 for here. Okay. So, and you got that by taking this. Okay. Now, do we want the sine of 31?
Don't you want the cosine? I was about to say, don't you
Okay.
want the cosine?
Is this 31 actually the angle between the lever arm and the force?
No.
This is the angle between the lever arm and the force. Does that make sense? Okay. Julie, the lever arm is just going to be this distance right here. Does that make sense? It's the distance from the center of rotation.
The cosine is 428.
Okay. Oh,
Oh. Do we have to add up?
seems big.
Yeah.
Yeah, I know.
Are you in radians?
Potentially. No.
Wait, so do we have to add?
So here, the angle here, when we plug it into this formula, is going to be 121, right? That makes sense?
Oh, that's fine. It's divided by
Wait.
10.
What?
42.86. Because I did 20 as the distance, not...
Okay. Okay. So here, that's the torque that this one's causing. Okay. Does that make sense? People that are still with me?
Yep.
What's your guess?
Say again? How do you want to go? Okay.
Wait, I didn't get that at all.
So Grace, when we look at this formula, okay, I don't know, I haven't done it yet, so I'm relying on you guys.
Can you write it out for me?
Sure.
once?
So,
Sorry.
Grace, here's our formula, okay? Force is force, distance is distance from the center. This theta is the angle between the lever arm, which is the distance from the center, and the force itself, okay? So this force is being applied like this, and it gives you an angle of 31 here, but that's not the angle between the lever arm and the force. That's the angle between this vertical line and the force. But that's not what we want. We want this, okay? But we know that this angle here, right, is going to be how much? Yeah, 90 plus 31, right? So when we go to calculate the torque, it's 25 times 2 times the sine of 121 degrees.
Whoa. Oh.
You could just do the cosine of 31.
Or you could do cosine of 31 as well. Yes.
Okay.
That would get you this actually get you the same answer.
So you don't like find the
No, because this horizontal component here passes through the center of rotation. So it's not going to cause any torque. Okay. So then down here, right, torque is equal to 10 times 4. Whoa, whoa, whoa. Times the sine of 113.
Because you have to,
No, wait, sorry, my bad.
Yeah, just the sine of
Sine 23 for that one. Sorry. I'm tired too.
how do you know when you need to change it? I got to
Actually, you could do sine of 23 for this, or you could do this angle here. That should get you the same thing.
I got. How do you get 121?
Okay. This one.
Yeah.
Okay. This is the angle that, sorry, I should change that back to blue. For the blue one, this is the angle between the lever arm and the force. Does that make sense? Okay. Yes, no, maybe.
Yeah, that's,
This angle here is 31, Marissa.
Yeah.
But we have to include this whole part of the angle, right? And that's how much?
oh, I know it's straight up and down.
Yeah,
I was looking
this dotty line is straight up and down.
I was looking at your blue line and I'm like,
So here, you can calculate it this way,
why
or,
did you whisper it?
because, should I give you a hint?
Oh, 90.
Secret
Oh,
like
I'm trying to figure out if that was a blue line.
7, okay? You could also do it that way, where you could get the sine of 157, because that's actually the angle between here and the end, okay? And you can multiply this all out, what do you get?
It seems like it's right.
Okay. So, this rotating object is going to spin this way, right? Counterclockwise based on the torque that we've calculated. Good there?
No, the top one has.
Okay, good. Top one is the biggest torque, yeah.
Just want to make sure it's.
So would you subtract those two torques if you wanted the net?
Yes. Yeah, if you wanted the net torque, you would have to, because Benji, we'll get into that a little bit more tomorrow, but yeah. This one's causing a rotation in one direction, this one's causing a rotation in the other direction, so that's going to be one's positive, one's negative.
And you can just subtract the torques, you don't have to like subtract the...
No, subtract the torques, because the torque takes into account both the force and the lever arm. So, all right.
We did it!
We're not done yet.
Well, I think there's only 15 minutes left.
16.
No, yeah, we're good.
All right. Let's take a look at a couple of conceptual questions off of that new sheet that I gave you today.
It's sick.
This is brutal.
One of our, like, game examples was that for,
Was it the ladder?
yeah.
Yeah. The ladder's torque one. So, yeah, all these windows can close all the
Yeah.
cool stuff.
A lot of
Supposed to be like 60 degrees. Protection.
What is that? Right there. Oh, I was like,
I think they're done.
they
What?
had them at one of the stations.
We'll get some money moving now.
So we can get the... Who's the manager guy?
I love that.
Oh, you don't want to miss the videos? Okay, good. So, all right. This question, number 4, applies to, has anybody ever been to a house that's kind of an older house, like houses that were built in the 70s sort of have this a lot, okay? where the door handle is right in the middle of the door.
I've never seen
Have you
that.
ever seen- Say again?
It's a nice.
Yes, sometimes front doors are like that. Like the door handle, instead of being here, is like right there.
That's
The worst
really
when someone's a
weird.
screen door and a regular door, it's like a screen door this way, and a regular door that way. It's annoying.
Yeah.
No,
I know what you're talking about.
I was talking about doors. Like you come to a door, it's like a regular screen door right here, and the other door like opens on the other side.
It's like an airlock.
I'm here.
All right. So now that Tyler's done ranting,
I'm talking about doors.
all right. If we look at a door from the top, okay, and this door is going to open like this. So here's the hinges.
Oh,
Okay.
this is like bird's eye view?
Yeah, bird's eye view. Yeah.
Oh,
Right.
okay.
And
Weird.
bird's eye view, right? And then here, this is Tyler's screen door that he was talking about, and his screen door is going to open this way.
Oh,
The
the
hinges
worst.
are like there.
We had a door like that when I lived in New York.
What?
It was like,
That's what you were talking about, right?
Yeah, that's
I think so.
Yeah, okay.
yeah, this one over here.
I ran into the glass door before. That's happened. Our dog always ran into that
Yeah.
door too.
Now, the screen door has its handle right here. Okay? So whatever, it's got the little button thing or power, okay? But the door to the house has the doorknob right here. Instead of
That's crazy.
right here. Okay? Aesthetically pleasing? Possibly.
No.
Okay? But
That's barbaric.
what's the problem? This is barbaric right here. But aesthetically pleasing, possibly. But by putting the door handle in the middle, right, it's harder to open. Right? If we look at our formula for torque, F times D times sine of theta, right? By putting the door handle in the middle, how far away are you from the center of rotation? Only halfway across the door, right? But if you put the handle way out here, what have you done to D in that formula now? Double it. Pretty close, maybe not all the way, but pretty close, okay? So, by making the lever arm shorter, right, you have to apply more force to produce the same torque, which causes the door to open. Okay? Another example, somewhat like this. Okay? You come up to one of those doors that has the bar, like a glass door to get out, you know? Like the doors like right here by the library, the ones that get you outside. They have like, you know, the push handle out, okay? And coming up to the door and you really don't know which side it is, so you pick, right? Yeah, it's always safest to use two hands. But so you pick, but maybe you're carrying something, you know, you only get one hand, right? But instead of pushing it out here, right, you push it here, okay? And you pick the wrong side,
You can't open
okay?
it.
It's not that you can't open it. How hard do you have to push to open it, though?
What is too hard?
You have to push a lot harder because now the lever arm is very short because you're very close to the center of rotation. So to produce the same torque to get the door to open, you have to apply a much larger force if you're closer to the hinges. Good there? All right, let's talk about some weird body things. Okay? Not like that kind of